and yeah, great to see the numbers on the call. I'm counting 117, so yeah, fantastic turnout, and yeah, hopefully you'll find this session relevant to your sort of daily sort of work sort of requirements, and obviously with the sort of steer towards climate change, which is something I'm particularly passionate about. Hopefully you'll see that come through during the presentation. So yeah, a bit of background very briefly on myself. I'm the rail lead at Tensar. I've been with the company just coming up to 10 years now, in sort of wearing various hats along the way in terms of sort of area civil engineer for the northern sort of central region, before sort of steering into the rail specialist part of our business over the last sort of 4 years or so. Over that time, Tensar has grown and changed ownership. We're now a division of the commercial metals company, FTSE 500 company, with yeah, their sort of toes in sort of various parts of the construction, civil engineering sectors. As part of that, we're working sort of more collaboratively, closely with some of our sister companies, including GeoPeer. So my colleague Bruce Bush is on the call today, who will be covering some of the specialist rail geotechnical products, which we're starting to gain some interest and traction for projects in the UK, taking the sort of the success, knowledge and expertise from the US, where this has become sort of quite common technology. So we'll move on to the sort of the body of the presentation. I'm going to be sort of really setting the scene for the topic of the subject title, and introducing to the general sort of problems that we're facing in terms of UK earthworks, based on sort of past practice in terms of its construction, the sort of the common failure mechanisms, and where sort of geogrid-based solutions are finding their place, before moving on to the sort of just say the more revolutionary approach available through the GeoPeer plate pile system technology. So as Stuart touched on, I'm one of the founding members of the PWI Environmental Sustainability Committee, which was formerly the Climate Change and Decarbonisation Committee. I see railway engineering as sort of integral to achieving the 17 UN Sustainable Development Goals. Since 2015, the publication of these Sustainable Development Goals has been an active global effort to reduce carbon emissions and create a sustainable future for our world's ecosystems. Much more is to be done to limit this environmental and ecological damage that the increasing levels of atmospheric CO2 will inflict on our planet, and alongside that, a need to adapt our railway infrastructure to be resilient in the growing challenge of climate change. Climate change is undeniable. It's here. 2023 marked the warmest year on record globally, and the 10th year in succession where that exceeds 1 degree above the pre-industrial period between 1850 and 1900. If we look at the trend of that alongside the sort of the extreme weather patterns, we can see a significant acceleration in terms of flooding events and storm events, which again happening on a global level, but very clearly being seen in the UK as well. So the focus of my part of the session is going to be sort of more UK sort of centric. So looking at the records and statistics here, we can see from 2022 this was the warmest year, with 2023 following closely behind in second, in terms of temperatures encountered in the UK. So obviously, yeah, the challenging nature of not just the wet weather, but the peaks in the warm weather is going to be, yeah, what we hear as sort of everyone dialing in on the call as sort of P-way, geotechnical, earthworks, sort of involvement are going to have to contend with. The fourth wettest 18-month period was recorded between October 22 and March 2024. Is when I originally pulled together this presentation. That those records were sort of quite fresh on that. And during that period, it was also a record amount in England. So yeah, you can obviously see even within the United Kingdom, we're getting certain sort of regions which are sort of being braced for events which are beyond any sort of historic level. So summing up those sort of previous 4 or 5 slides there, we can see ultimately what that sort of trend is sort of leading towards: warmer and wetter winters, followed by hotter and drier summers, and importantly, this more frequent and increased intensity of these weather events. So yeah, I think everyone on the call dialing in today will be aware of certain earthworks failures and some of the drivers which may sit behind those, but all sort of loosely linked to what you can see in these trends here, increasingly what we're going to be up against. Putting that into context, so we have a bit of background there in terms of the climate that we're dealing with, but also what in terms of our existing assets are we. Someone else is now in control of the presentation. Sorry, is Michael Baxter? Sorry, I think you're taking control of the presentation. Let me try sharing again. So Stuart, can I get a thumbs up if the presentation's coming through again? I think there was an issue with someone taking the slides control. Was it Michael Baxter? I think I had come up.
You're back up. That's great. I've never had that instance before. That's an interesting one. So please,
I think it's happened again. Is it Michael Baxter?
You can obviously see something I can't then.
Yeah, looks like someone's taking control and then moving the cursor around and taking the notes away.
Right, can you grab control back? I've got something on a screen here that says take control. So no, that's not going to help. Right, you knew who it was. Can we ask the gent who it was to log off, please, and perhaps log on again if we got a problem? Peter, you can see who it was.
Yeah, I think it was Michael Baxter. So yeah, I may have just done that accidentally. So yeah, we'll crack on if everyone can see the slides again now.
Yep, now Peter.
Okay, all right. Apologies about that. So as I mentioned, that yeah, the climate, we've got a bit of background on that, and so what the trends are sort of telling us, and what we're going to be sort of increasingly up against. Now we're just trying to understand in terms of the earthworks, the assets which we're sort of managing and sort of maintaining. What is the sort of the background and sort of the history of that. So Network Rail manage approximately 190,000 earthworks assets, that being comprised of around 70,000 soil cuttings and 100,000 embankments, and obviously sort of rock cuttings and so on beyond that. A lot of this was the construction was done during the Victorian age, so the sort of the 19th century, which was really prior to the development of formal soil mechanics and geotechnical engineering. So many of these were constructed by sort of end-tipping material excavated from further afield in a method called cut and fill. So basically high ground was excavated and the material was used to raise up low ground to produce level track. So this is something which Thomas Telford and obviously most modern engineering practice would disapprove of. Obviously end tipping, loose backfill, and the sort of the increased consolidation time is going to cause issues with the the stability of the earthworks, and then obviously over time the sort of the slope stability, both for the sort of the steeply excavated cuttings and then the upfilled embankments. So yeah, what was seen as best practice or sort of most economical and the speed of construction back then has obviously left a legacy of sort of challenges for the operators of sort of the rail lines to contend with. Rail earthworks is a massive subject, and various sort of publications sort of available, which give sort of deeper insight into the sort of the means of this construction practice and sort of how it evolved from the sort of the 19th century into the 20th century, but again with certain issues and sort of failures addressed, which obviously exacerbated by the influence of climate change. Just drawing attention to a PWI journal published in July of last year. I'm not sure if Tony is potentially on the call today. I had a sort of a quick run through with him prior to the development of the initial sort of webinar content, and he was very sort of useful in sharing his knowledge on the subject. But this, a great piece where the earthworks assessment for the impact of soils vulnerable to seasonal cycles. So wet winters and dry summers will influence the annual pore water pressures. So higher at the end of winter, lower at the end of summer. These cycles cause an outward movement, strain softening, and ultimately slope failure. So anyone on the call who may actually be sort of working along the West Coast Main Line, a very sort of useful journal to be aware of and gain a deeper insight in that specific region. The roots of some of these issues and some of the means to overcome them. Another very useful publication is the Network Rail Review of Earthworks Management, which again highlights, to no great surprise, the strong correlation between earthworks failures and rainfall between the cycle of 2003 to 2020. So in a particularly high rainfall period between 2019 to 2020, there were 252 Network Rail reportable failures. So 130 soil cuttings, of that proportion, a higher proportion being shallow translational failures, and of the 62 embankments, again a higher proportion being aligned to a rotational failure, with a sort of a low amount linked to shallow translational failures. When this is compared over a sort of a longer duration, so the mean from 2003 to 2020, we can see that during this peak sort of rainfall period, the number of reportable failures increased by a magnitude of 3 for the cuttings, and magnitude of 2 for the embankments. So interesting to see that correlation and the influence that this is having. So failures generally occurring after prolonged periods of rainfall in the winter and after intense rainfall in the summer months. But of the deeper rotational failures, these were occurring largely in the heavily consolidated plastic clays in the South and Midlands, whereas the shallow translational failures and washouts were sort of more spread across the network. So from the cutting failures, these are actually more likely to cause derailments due to sort of the clear obstructions on the track. So yeah, obviously we don't want to be in the case where the train driver is actually seeing an obstruction on site, but obviously it's the most visible and potentially the one which is going to be the highest risk to sort of immediate safety. Embankment failures tend to cause a loss of track support. Often this is not a sudden loss of track support, and may be identified in track quality measurements. So an important note on that one as we go on to sort of the further slides about PWI engineers essentially picking up some of these trends before a sort of a more deep-seated earthworks failure may be encountered. So an interesting sort of case where you can say this did happen on the Hook embankment failure back in January 2023. So a track defect had been identified a couple of days earlier with sort of relatively minor repairs by sort of lifting and packing of the track. Unfortunately, the PWI engineer had not associated the track defect with a potential earthwork failure. Obviously, over the sort of the subsequent sort of 24 to 48-hour period and above average rainfall, this contributed to a shear failure of the clay embankment over the softer alluvium soil. So obviously, this was a significant failure, causing disruption along the main line there. One of the sort of the tracks closest to the crest of the embankment being completely closed for an extended period, and obviously line speed restrictions on the other, while they went in to sort of carry out the emergency repairs, as you can see on the image on the screen there. So again, highlighting that importance of identifying these issues early enough, because we know that the cost implications of this, that if we're treating this as an emergency repair as opposed to sort of planned maintenance works, the cost increase, as what we can see from this reference from the Syria report, is by a factor of around 10. Obviously, that will change sort of project to project, but if we can work sort of collaboratively, use sort of the likes of INSAR satellite sensing technology to look at where there may be sort of signs of sort of movement and serviceability issues, then we can look to sort of go in with the appropriate reinforcement, stabilisation solutions, either as a sort of a temporary fix or a sort of a larger scale renewal, which will in the long run sort of ensure sort of resiliency and sort of the robustness of that section of track and avoid any sort of major disruption along the main line. As we move into control period 7, so that's from April 2024, climate change has been sort of firmly fixed in the plans there. So of that £45 billion 5-year investment, a significant sort of effort will be made on ensuring our railway faces are going to be sort of up to the challenge, making them more resilient, with thousands of miles of drains, cuttings and embankments being set out to be more weather resilient. So that being comprised of around 20,000 cuttings or embankments which are in need of attention, and 300 miles being strengthened through renewal and refurbishment. So a significant sort of 4 or 5 year period ahead of us, which we can hopefully from sessions like to this share experience, knowledge, expertise, new ways of working to ensure that we're providing something which is going to be resilient as well as economical, so we can make these funds stretch further. Sorry, just skip this slide. So just after sort of setting the scene for the subject, really just moving now into a bit of an overview of Tensar and our sort of work in the rail sector. So we cover a range of both temporary and permanent work solutions. So projects such as High Speed Rail 2, which is effectively just a large infrastructure scheme. We've been involved with sort of the various setup of haul roads, compounds, piling platforms, crane lifting platforms, temporary overbridge, which then leads on to sort of the more permanent works activities, where we may be involved with our reinforced soil bridge abutments, steepened cuttings and embankments, as well as providing our geogrid-based solutions directly into the track bed layers to either sort of reduce sort of upfront costs or extend the serviceability of the track bed build up. So we did provide a webinar probably around 18 months, 2 years ago now, covering our geogrid-based solutions within the track bed construction, if anyone wants to look back at those. But really, for the purpose of today's session, we're going to be focusing on our reinforced soil geogrid-based embankments, cutting solutions, as well as introducing you to our sister company, Geopia, who have their SRT plate pile system. So we'll, I won't sort of hold on that one, but we'll, that'll be the sort of the main product areas that we're going to be exploring into. And just to flag up, we do have the Railway Industry Supply Qualification Scheme audited status for our design services, as well as the verified status for supply of our product systems. So where consultants or contractors, clients want to work directly with Tensar or sort of sub-consulted packages, we can carry that out under sort of our own umbrella, and provide the design services backed by the industry requirements. So on to sort of earthworks and sort of the definition of that before bringing that into where our geogrid-based solutions are brought in. We can see the extract from the relevant network rail standard that an embankment, cutting or natural slope or nailed, reinforced with, importantly, a face angle of less than 70 degrees. So BS 8006, the code of practice for reinforced soil and anchored soil systems. We can see common scenarios there. So a new construction, upfill embankment, as shown in Figure A, or sort of more commonly for repair of existing embankments or cuttings, where we'll be excavating into the existing construction and incorporating the geogrid reinforcement layers. The common types of failure where our solutions are being brought into a duress can be seen here. So sort of shallow creep, sort of near surface soil desiccation over time from the seasonal swell shrink cycles, as covered on the PWI journal that I referenced earlier, where this is sort of materializing. You can see if there's sort of an intense rainfall period following that, then we can start entering a sort of a condition where we're likely to experience slumps and earth flows. So this shallow translational failure resulting, if this is a cutting, for example, with an obstruction on the track, or a gradual sort of loss of support to the rail track line, if that was an embankment. And then beyond that, we've got some more sort of common geotechnical translational failures in a shallow slip circle, or a deeper seated rotational failure, which may be looking at sort of more heavy based sort of sheet piling solutions to address the sort of the mode of failure there. So many of you on the call may have seen this in practice. Some of the types of signs that might be being given as we start to see the gradual loss of support to the rail track. So sort of soil mass sliding along the slides, or affected bulging of the upper track bed construction, where we're starting to see these signs of movement and serviceability issues. Common repair solutions that we may be looking at here, simple sort of regrading and benching, which may include incorporation of the geogrid reinforcement layers, particularly if that's going to be incorporated using the actual failed material itself. This image to the top right being sort of general sort of riprap and effectively surcharging the face of the slope to provide that stability. And then for larger slopes, we're looking potentially at sheet pile systems, for instance, and sort of regraded crest slope, as well as the soil nails being sort of quite common practice in the UK. reinforced soil, so where we're sort of providing our geogrid-based solution. I just wanted to give a very quick recap of where this technology started and the experience gathered sort of along the way to sort of where we are now, with it being a sort of a relatively accepted approach. So they did the first trial of this being back in 1980 for a geogrid reinforced soil wall, which happened to be in a rail environment. So the Newmarket Silkstone Colliery near Wakefield. The requirement was to support and to reconstruct a failed embankment with a reinforced soil wall system using the available marginal quality fill. So the colliery spoil was used on site, built up in layers between the geogrid reinforcement layers and a precast concrete facing. I always find it a little odd, sort of looking back through the sort of the history of our reinforced soil applications, that the first immediate sort of full scale sort of construction of this was supporting a rail track, which you would generally consider as sort of quite high risk. But again, this was sort of justified at the time, and again the sort of the demonstration with this being included as a Tomorrow's World program at the time, so seen as this sort of revolutionary piece of plastic which was going to sort of reframe the sort of the civil engineering construction practice. There was a lot sort of riding on this, if you like. The performance exceeded all expectations, with no discernible settlement in over 3 years of monitoring. And again, this wasn't a sort of a car park retaining wall with sort of negligible sort of surcharge above it. This was having around 300 ton of sort of waste and sort of carriage passing along the railway every hour. So it really puts to its limit from an early stage. If you click onto YouTube, Tensar Tomorrow's World, you'll find a sort of a couple of minutes video going into a bit of detail on the sort of the building construction and the actual setup of it. From the sort of the early sort of invent of reinforced soil walls, we also ran that alongside this being used without a formal facing for more shallow slopes. So sort of shallower than 45 degrees, we don't include any sort of formal facing other than a sort of erosion control matting. So quite common in a rail environment. We can see along that right hand side a typical slip repair system approach, where once we've addressed the slip circle failure, we're simply excavating and benching it as would be done with sort of traditional earthworks, and then incorporating the layers of geogrid reinforcement, with again the sort of the real benefit where we can use reuse the failed slope material back within the compacted layers and ensure that is back to its serviceable state. Obviously, the material needs to be compactable, and we're within a certain sort of range of geotechnical soil properties that we can work with. But yeah, where this can be done, we're obviously removing the need to import significant quantities of sort of quarried aggregates, for instance, and obviously the disposal and potential offset into landfill. From 45 degrees up to 70 degrees, we can also sort of serve that requirement with generally a steel mesh facing, which would be fabricated to the base of these units. So as you can see on the image there, simple connection through a bodkin at the base of the steel mesh unit, and sort of lightly tensioned back and layers of fill brought up, with construction wholly within the face. Various case studies available. This one down in South Wales, constructed up to around 20 metres in height, and again comprised wholly of a local colliery spoil material. So that avoided around 150,000 tonnes of carbon from that particular scheme. And on the sort of the community sort of local impact side of it, around 7,500 lorry movements removed from local roads. We also have the environmental product declaration for all our GeoGrid products. So these can be included within sort of various rail carbon tools. So you can show what the actual benefit is in comparison to sort of a more traditional solution. Again, different types of facing available. Generally, we're favouring a vegetated system, but where sort of ongoing maintenance may be problematic, we can offer a hard-faced sloped concrete block system. Where we sort of know, other than sort of some of the case studies which we touched on there, we've been able to work with sort of independent government bodies to actually quantify what the savings are on a general project. So the RAP government sort of led Geosystems report from, I think it's back in 2005, 2006, gave a run through of a traditional L-shaped precast reinforced concrete wall against a sort of a value engineered option of a tensile reinforced soil wall system. The outcome of that was that the carbon saving on the project, taking into account the fill materials and the actual system components, resulted in a saving of around 57 to 80%, and in terms of the cost, around 53 to 75%. So significant both on the carbon and the cost side. And we have published a recent paper for a HS2 bridge abutment, which saved 66% carbon against the original sort of consultant-based design. So coming towards the end of the sort of the Tensar product area, this is a sort of a very sort of useful overview of our sort of related product systems, where we've got the track bed and then the geogrids within the sort of the steep and embankment sections. We're now going to touch on the SRT system from GeoPeer, which is a sort of a revolutionary approach, really, and another sort of feather to our cap, really, where it's not practical to have that excavation and sort of excavation past a slip circle and filling back up below the embankment, because of the sort of the line would have to be taken out of service. With the SRT system, we've got the benefit where potentially there will be very minor excavation required, installation of the plate pile system, which allows us to keep the line operational and running. So I'll move on to that now. I'll continue to go through the presentation, but I've got my colleague Bruce on the line, who will be chipping in as and when required, and will be available for sort of more technical questions at the end of the presentation. So in essence, that this is the sort of the elements that we're dealing with, and where we're going to be driving it into the earthworks. So the plate pile, it's a steel channel with welded plates fabricated to it, sort of varying sizes depending on the sort of the depth of the slide failure identified. So this will be driven into sort of a semi-competent sort of subgrade soil, with the upper, should I say, less competent or sort of more loose superficial layers being sort of constrained by the upper welded plates. So these plate piles effectively resisting the sliding force of the sort of the upflow soil mass. So different to what we're seeing for, say, a sheet pile, which is sort of continuous at a certain level. What the plate pile system is doing, it's dividing the slope into small increments. So at the appropriate spacing, so typically sort of 1.2 meters by sort of up to 3 meters, by the influence of the soil arching between these plate piles, we can sort of maintain that consistent level of reinforcement and stability up the slope. Where that can have benefits, so in a rail environment here, we've got the flexibility that we've not got a continuous barrier as such. So these can be positioned to suit the sort of the earthworks alignment and sort of interface with drainage and so on. So yeah, again, with the sort of the drainage characteristics of that, we're not restricting or resisting the sort of the passage of water within the earthworks. The applicability for the system, we're really looking between sort of a 1 in 3, 1 in 1 slope arrangement. That I think there's experience beyond that, but generally that is the sort of the sweet spot, and a slide thickness for that shallow translational failure of sort of between around sort of 3 to 5 meters being a maximum. The stable soil which the sort of the steel channel is going to be sort of driven into would really be a soil with you know, a particle size of less than 75 mil diameter, and yeah, sort of suitable soft rocks and sort of firm stiff clays being suitable. There has been limited sort of experience where encountering hard rock where they can sort of pre-drill and sort of grout it in. But generally, yeah, sort of less common where we're dealing with that type of condition. The installation, again, relatively sort of straightforward in terms of the plant equipment that would be using. So an excavator with sort of a suitable attachment. So once the sort of the positioning and sort of setting out of these are in place, then a simple sort of driving mechanism into the stable composite layer. Hopefully the video came through then, only a couple of seconds. I'm happy to sort of share a link after the presentation. But yeah, you can see the sort of the speed of the installation is rapid on this. I think I've got a slide towards the end with an indication of sort of the installation rates with this type of system. So before we do anything in terms of the installation and sort of setting out the required information which we need to develop a proposal is sort of as set out here, and as what you might expect for any type of earthworks slope solution. So importantly, that depth of slide. So we understand whether it is a shallow translational failure. If it's a more deep-seated failure, then yeah, it's probably not our bag, and yeah, onto maybe a more traditional sheet pile solution or otherwise. The soil exploration, so we need to have a good understanding of the ground conditions, so boreholes, CPTs, etc. And yeah, the slope inclination. So if the slope is actually already sort of had the slide failure, then yeah, an understanding if any of what those sort of related measurements would be, and yeah, an accurate understanding of the sort of the layout of that. So the operation in the US, where again this technology has been around for, Bruce will correct me, but well over 10 years, up to sort of 15, 20 years, I believe now. They have sort of good relationships directly with contractors where these are being used on the sort of the rail network, and yeah, where there's a sort of a need to address an emergency failure, for instance. There's sort of standardized chart solutions for quick responses, and yeah, typically dealing with lower risk, so less than 3 meter slide depth, where they'll use standard sort of stock available elements, and they will sort of within sort of 12, 24 hours, they can get onto the network, provide the installation, and yeah, maintain the serviceability of that rail network. Obviously, in the US, the rail network is vast, and it's not just sort of through sort of public ownership. It's the sort of the private sort of freight lines and so on, where yeah, these type of solutions are very sort of valuable and sort of practical for them. Where they're getting involved with sort of design and build, sort of more complex and possibly larger projects, then they'll provide a site-specific design solution. So using sort of very slope stability, finite element analysis to provide an efficient, optimized sort of layout of the plate pile elements. So yeah, again, from what you can see there, we've got the simplified chart solutions, which again we can share and sort of give confidence that yeah, we will go on the sort of the cautious side, and that will allow the operational line to continue, and we're effectively increasing that factor of safety from what should be close to 1 or less than 1 to an acceptable sort of level of sort of 1.3, 1.5. There's a lot of validation and sort of verification testing which went sort of before all this, before it started to become common practice in the US. So full scale sort of testing, which was then sort of run through 3D FEA analysis, and then yeah, physical trials to sort of back up the sort of the results on that. So yeah, the sort of the spacing of the plate pile elements, these need to be appropriate to resist that sliding force between the soil mass of those rows. So yeah, the sort of the calculations which sit in the background can work out what that soil arching effect will be based on the type of fill material that it will be interfacing, and then set out what that appropriate spacing would be. Okay. So yeah, with this is from the test trial which they did in the US. So yeah, a full scale slope was constructed approximately sort of 1 in 2, and there was a concrete sort of initial layer, so a relatively sort of smooth layer to sort of start to sort of incur that failure. So that was done sort of with and without the plate pile elements, and it was subject to sort of the infiltration lines, so the water coming in to induce that failure, and then the results sort of recorded from that. So yeah, you can see from that sort of controlled infiltration, both below the slope and from on top, quite quickly we can see without the plate pile elements, there was a failure within 7 minutes. So yeah, obviously from the records of that, we can see what the control section would be. And then once the SRT plate elements were incorporated within the second test setup, we can see a very nice visual there, seeing what that soil arching is happening in practice. So the initial trial was not able to actually fail the slope. They then allowed this to sort of dry out over the sort of the summer period before then sort of resaturating the slope to try and induce that failure. So yeah, from that, the SRT elements, because it was still not able to induce that failure, were removed, and quite quickly after that, the failure occurred. So yeah, again, I'm sure Bruce could go on spending an hour talking about that particular section of it, and if there is more interest on the call, then happy to address that sort of offline, or if we've got time at the end of the presentation. So the structure for the development of the design, we're taking that factor of safety from the slope from close to 1 to above that. We can initially run that through based on the standard design charts to get an indication of what the likely plate pile length and spacing would be, and then we can run that through the Rock Science pile design software to get an idea of the sort of the force requirements and on that laterally loaded pile. So you'd be designing that to a serviceable pile deflection and the maximum bending moment, so we can ensure that we've got the appropriate sort of steel grade in use. That would then be run sort of as a control, and then with the plate pile elements through the Rock Science slide design software, so we can show what the sort of the outcome would be for the sort of the final factor of safety for that earthwork. An example here. So again, there is a a project in the UK that we're looking at with input of Bruce at the moment, where we're sort of evaluating that with a factor of safety sort of close to 1, and following the assessment through rock science pile output, we've been able to provide an optimized arrangement, and that's resulted in now a factor of safety above 1.5 based on the sort of the site specific conditions. A very quick sort of just run through 2 or 3 US case studies here, just showing it in practice on rail projects. So a site here where this was actually used as a temporary solution to build a permanent reinforced concrete wall in front of it. The speed of installation on this one being key, so 100 plate piles over 5 days with sort of the relevant setting up and sort of decommissioning on that. That's a pretty quick installation. Another sort of similar job here with plate pile elements being installed, 650 plate piles within 10 days. So obviously a good level of output there, and this was supported behind a sort of a row of gaping baskets at the toe of that, and a sort of a larger sort of highway scheme there as well. Again, we're talking rail today, but again, used in other areas as well, with 150 plate piles, 3 meters in length being applied for a relatively shallow 1.5 meter depth on that one. A lot of the sort of the potential and sort of the interest which we've seen is for sort of more emergency works and rehabilitating existing slopes. But again, there's the potential that we can use this to steepen up slopes to maximise land usage at the toe of the slopes. If there's a new development or a need to steepen up to add another line closer to the edge of the existing embankment. So lots of additional sort of side benefits which we can explore on that one. So coming to an end on this presentation now, we can see the sort of the benefits of the sort of the plate pile system technology against other maybe more conventional systems. So again, I think making the industry aware of the technology and having it as another option is certainly going to be a positive. And from the initial sort of throws we've had on a couple of UK projects, there's definitely some benefits to be made there. Final slide now. Hopefully for those of you maybe familiar with Tensar but not of our sister company Geopia, a bit of an insight to sort of the wider sort of portfolio of rail earthworks product systems which we've got available, and ultimately I think with the sort of the challenges that we're facing from climate change, we're going to need to have every sort of tool available in ensuring that we've got resilient options and solutions to maintain the operational running of our rail lines. So hopefully that was useful, and myself and Bruce will be available for any questions you may have.
Peter, thank you very much. Very informative, very useful presentation. Certainly, as you mentioned in your introduction, the sort of things you've been talking about are things that we will face more and more and more as the climate change hits us more and more. So thank you very much for the presentation today. I'd also like to thank Bruce, because although some of the questions were going up and I was going to pose some questions, I think Bruce has been answering them as he's gone, which is great. So certainly, Mark, I hope the answer that Bruce has given you online is what you're after. There's a thumb up. I assume that's probably you. And I'd also point out that early on you showed some information regarding where was it? It was Skempton. And Angela was great in posting very quickly the document that you referred to. So anybody wants to go and see that, we will post that on the LinkedIn site, or the PWI LinkedIn page, so that you can go and get that if needs be. I think in reality that's answered all the other questions that have appeared. So if I may, I'll just ask one. But if anybody else wants to add any on while I'm here, please do. Peter, you mentioned that there was 45 billion that was set aside in the next control period for rail improvements associated with climate change. Are you seeing any of that filter through, or are there quite strict rules in terms of what that might be applied to? How's it sort of feeling from your end?
Yeah, I might just need to clarify that 45 billion is the overall investment for control period 7, so that 5-year sort of allocation of funds. And yeah, it's been highlighted that within that, climate change is sort of a high priority and probably the biggest challenge facing the network. So it's not 45 billion pounds exclusively to deal with climate change, but yeah, obviously that is going to be part of it. In terms of the start of this control period, so from the beginning of April, in terms of what we're seeing in the industry, it's very slow, quite sluggish, and I think that's sort of quite consistent with some of the feedback we're getting from sort of the consultants and contractors. But certainly, hopefully as we get towards the end of year 1 and sort of into year 2, where hopefully sort of designs are starting to sort of develop and funds starting to come through and be spent, then I would hope that we were going to see a significant ramp up.
Okay, thank you, Peter. I think Bruce has been busy again answering questions that have just come up. I think Alistair asked the CRT system, what's the design life? And if I've read this right, Bruce has said typically 50 years. Bruce, if you'd like to come on and add to that if necessary, or is that how you saw it?
Yeah, from my sort of experience sort of dealing with Bruce over the last sort of 12 months or so, where in the UK we have sort of a general 60 years design life for earthworks, 120 years for structures. In the US, they tend to have 50 years for their earthworks and 100 years for their structures. So again, that's not saying we're restricted to 50 years, but yeah, that's sort of where the background and the experience is in the US. Where we need to possibly thicken the sort of the plate, then we'd be able to satisfy 60 years, which is typical for earthworks.
Okay, and given we're just about time, just last question on that. Azim has asked, is there still really a steel enhancement required to use the SRT system, i.e. does it need to be galvanised, stainless steel based on standards? Any sort of comment on there?
Are you still on the call, Bruce? Do you want to chip in on that one?
Yes, I can answer that. So typically we just use black steel. What we do is we actually specify 50 KSI on the actual S or C channel sections and 36 KSI on the plate. And if you're in a corrosive soil, typically what we'll tell you to do is just add a couple of millimeters of thickness to the elements to gain some design life. Now, that to answer that question on the design life in the U.S., what we use for the 50-year design life is we actually look at the worst soil conditions whenever we attach that 50-year design life to these. So that's typically in a really corrosive soil. So generally speaking, if it's a non-corrosive soil, we've ran the numbers on them, and typically we get upwards of 75 years. But just from a standpoint of what we tell people in presentations is typically 50 years in the U.S., which is kind of the standard there. So
that's great. Thank you, Bruce.
Yeah, and as far as enhancement, yeah, you can do them in galvanized if you want to. We don't do stainless. That would be very, very expensive. And galvanization adds quite a bit of cost to them too. So if you're in a corrosive soil, the easiest thing to do is just add thickness. So.
Right, that's great. Thank you, Bruce. Right, I think I'll call it to a halt there. We've had a good hour, which is great. So many thanks for that. Just to remind everybody that you can continue the conversation if you'd like to. We will have a dedicated LinkedIn page, so it will still be available to Peter and Bruce. So you can pose questions and they can answer them accordingly. So please feel free to make that conversation go on if you have a specific question that the guys here could answer. I'll just remind you that the next Lunch and Learn session in 2 weeks' time is about leveraging LinkedIn to make the most of you as a person or you as an engineer in terms of the social media profile and impact that you have. So that looks like it'll be a very interesting session. So at that point, so once again, thank you to Peter, thank you to Bruce, and everybody. I hope you enjoyed it. Hope it was informative, and hope to see you at another one of these in the very near future. All the best, everybody.
Thanks, Stuart.
Thank
you very much, Bruce.
Thank
you.
Take care. Thanks, Peter. I think it was a good turnout, Stuart.
Yep, it's good. I got to, I think, about 128, but when I see the official figures, it will be some more because it always is. And I'll confirm that to you in the next day or two once I've got that information. Thing is, it always requires everybody to log off before I get that, and sometimes people are just logged on for a while.
Yeah, no problem. Yeah, I think it was just that little issue in the middle. I'm not sure if that's something you can look at for future ones, whether they can take control. I've never noticed that before. I don't know how you do the settings to restrict it.
They're very interesting because I've never seen that before, and I've got my computer on. Plus, I've also got an iPad on to look at, and my iPad said I could take control. I've never seen that before.
Right.
The computer didn't, but the iPad did. So I wonder if that's a quirk. So I'll take a note of that, and we'll have to see if there's anything. But never seen it before. Never seen it before. Never been a problem before.
Okay, no problem. Well, yeah, there's always a first, but yeah.
Just it had to be yours, of course.
Yeah, but it was only a very minor thing anyway. So yeah, thanks again for organising it, Stuart, and yeah, we'll be in touch. Is the next committee meeting next week? Is it?
It's about 3 weeks' time, I think.
Is it 3 weeks' time? Is it right?
It's early November. So yeah.
All right, perfect. I'll catch up then. All right, thanks, Stuart.
Thank you. Cheers.
Cheers now. Bye-bye.
Okay, if you're still on, you can stop the record because I don't think I can. Yes, I can. I can stop recording. There you go.